In this unit, we're going to be looking at another new type of reaction. So we're going to be studying oxidation reduction reactions, also known as redox reactions, which are electron transfer reactions. So in a redox reaction, you have an electron being transferred from one atom or one molecule to a different atom or molecule. And we can really think of redox reactions as two opposing processes, oxidation and reduction, that always need to happen together. So oxidation is what we call it when something loses electrons. This E- is a symbol for electron. I can't remember if I've used that in earlier videos or not, but you'll be seeing it quite a lot in this unit. And reduction is when something gains electrons. So electrons always want to be attached to some atom or molecule. So when an electron is lost from one thing, it is always picked up by something else under normal circumstances. So these two things must always occur together. If something is oxidized, something else is getting reduced. Hence why we consider oxidation reduction to be one kind of reaction, because we really have these two things, but they always happen together. So we're always thinking about what is getting oxidized and what is getting reduced. And the way that we identify that is through what we call oxidation numbers. So oxidation numbers are really just used to keep track of electron transfers. Or electron movement. When something's oxidation number changes, that means that we gained or lost electrons, that it underwent some kind of oxidation reduction process. So when our oxidation number increases, that means that we have lost electrons. Means that something was oxidized. When your oxidation number decreases is when something was reduced. So essentially the way that we determine what was oxidized and what was reduced in a redox reaction is by looking at the oxidation numbers in the reactants and in the products and seeing how they change. Whatever element increases was oxidized and whatever element decreases was reduced. So our goal for this video is to learn how to determine something's oxidation number. So our oxidation numbers are assigned according to a series of rules, which I have here on the left. I did not want this G to come with me. Oh man, I'm bad at writing today. Following a series of rules. And these rules are a hierarchy. It is really, really important to remember that. So essentially these rules, which I've got right here, are, for the most part, the preferences of various elements. Certain elements tend to most commonly have certain oxidation numbers, but they don't all have an equal strength of preference. Some things have stronger preferences than others, and not everything can always get its way. Not everything always gets to have its preferred oxidation number. So you always want to consider these rules in order. Rule 0, just telling you that the rules are a hierarchy, so anything at the top supersedes anything over the bottom. Always consider them in order. Rule 1 tells us that the sum of all of the oxidation numbers for the atoms in a molecule or ion must equal the charge. So if you're talking about a neutral molecule, all of your oxidation numbers have to add up to 0. If you're talking about an ion with a -1 charge, all of your oxidation numbers have to add up to -1, whatever it may be. The rest of our rules are our specific preferences. Fluorine prefers to have an oxidation number of -1. That is a very strong preference over any other element. Rule 3, metals of group 1A, that's the column all the way on the left-hand side of the periodic table, prefer to have an oxidation number of +1. Elements in group 2A, which is the one right next to it, prefer to have an oxidation number of +2. You will notice that these are the same as the preferred charges that these things tend to form in ionic compounds. So the oxidation number is not the same as the charge, but it is often related to the charge. Hydrogen prefers to have an oxidation number of +1 when it is bonded to a nonmetal or a metalloid, which is by far the most common situation. Very rarely it bonds to a metal when it prefers to have a -1 oxidation number. Oxygen prefers to be -2. Group 7, which is the halogens, fluorine, chlorine, bromine, etc., prefer an oxidation of -1. Group 6 prefers an oxidation number of -2. Group 5 prefers an oxidation number of -3. So you probably want to pause here for a moment and copy all of these down. And now we're going to look at a whole bunch of examples, I think is the best way to get a feel for how to use these. So first examples, Fe, F2, and Mn2+. So these are starting out really, really simple. All we actually need to answer these is rule 1. Since we only have a single element, the only thing we really need to worry about is that the sum of our oxidation numbers for all of our atoms is equal to the charge. So in a case like Fe, there's only one atom and its charge is 0. So our only option is for that oxidation number to be 0 as well. So pink is going to be my oxidation number color going forward in my examples here. Similarly, for the Mn2+, there's only one atom. It has a +2 charge. If all of our oxidation numbers add up to +2, our oxidation number has to be +2 as well. For our fluorine here, same idea. We have 2 atoms though, but they're the same element. And for the purposes of this course, we can assume that all atoms of the same element have the same oxidation number in a molecule or compound. This is not always true, especially when you get into organic compounds with lots of different carbons. The carbons tend to all be different. But for the things that we will be working with, this will generally be true. So if they have to be the same and they have to add up to 0, they both have to be 0. So when we're assigning oxidation numbers, we are assigning them to each individual atom. So each fluorine atom has an oxidation number of 0 in these examples. So next up, CF4 and IF3-. So for these, we have to figure out each different element, what its oxidation number is going to be. So we want to check and see, do any of these elements have a preference? So for our first example here, we have carbon and we have fluorine. Carbon is nowhere to be found in our list of preferences, but fluorine is rule 2. Since carbon doesn't have a preference, fluorine gets to get its way. It gets to have its preferred oxidation number of -1, and that is on each atom. And there are 4 atoms of fluorine in this molecule. So in order to figure out the oxidation number of carbon, we're always going to go back to rule 1. For whatever our last element is, we have to satisfy rule 1, no exceptions to this one. This one takes precedence over everything else. The sum of our oxidation numbers has to equal the charge. Our charge is 0. If we have 4 atoms with a -1 charge, with a -1 oxidation state, that means that carbon has to be +4 in order to satisfy rule 1. For this one, we have fluorine, we have iodine. Fluorine, we just discussed, has a preference of -1 according to rule 2. Iodine is in group 7, so it also has a preference of -1, but it's all the way down at rule 6, so it doesn't have as strong a preference. Fluorine is going to win this battle because it is higher up on our list. Fluorine gets its way, having its oxidation number of -1, and there are 3 atoms of fluorine in this ion. The charge is -1, so our oxidation numbers need to add up to -1. We currently have 3 atoms, each with a -1 oxidation number. So in order for our sum to be -1 for the whole molecule, the iodine must have an oxidation number of +2. So we can see that that is not its preferred oxidation state, but that's fine. Not everything always gets its way, and that's why we have this hierarchy, these rules in a particular order to tell us who wins what battles. Fluorine wins all the battles, basically. Iodine does not here. So next up, I'll put up a few. So we have CH4, MnH2, NaOH. First one is pretty straightforward. It's very similar to CF4, just finding our rule for hydrogen here, which prefers to have an oxidation number of +1 when bonded to a nonmetal or metalloid. Carbon is a nonmetal. So that means that the hydrogen is going to have its preferred oxidation number of +1. There are 4 hydrogen atoms, each with an oxidation number of +1, meaning that in order to satisfy rule 1 up here, the carbon has to be -4 in this case. So we can see that carbon's oxidation number can vary pretty considerably. +4 to -4 is actually its maximum range, but it can be anything in between there as well. So it has lots of options and it doesn't really have a preference. In our next example, MnH2, manganese is a metal. And we see that hydrogen has a different preference for when it's bonded to a metal. So it prefers to have an oxidation number of -1 when it is bonded to a metal. This doesn't happen often, but it does happen. So in this case, it is going to have an oxidation number of -1. And there are 2 atoms of hydrogen in this formula. So if each of those has a -1, in order to satisfy rule 1, that means the manganese must have an oxidation number of +2. Our next example is one where hydrogen is in a formula that contains both a nonmetal and a metal. So what you have to actually be thinking about is what it is directly bonded to in the molecule. And ideally, you could draw out a structure for it, but you don't actually need to, is the thing. Hydrogen bonding with a metal is very rare and it is not terribly stable. So if there is a non-metal available for hydrogen to be bonded to, it will be bonded to the non-metal without exception. So hydrogen always prefers to bond to a non-metal when they're available. And if you looked at the structure for this, that is correct. The hydrogen is bonded to the oxygen, not to the sodium. It does not necessarily matter what it's written next to in the formula. Sometimes you'll see an H like sandwiched in between a metal and non-metal in certain formulas. It matters what it's actually connected to in the molecule, and that's always going to be the non-metal if there's one anywhere in the formula. So that means that hydrogen is going to have its preferred +1 here. I actually did these out of order, should have assigned sodium first. It won't turn out to matter, but rule 3 actually includes our group 1A metals. So that actually takes precedence over the hydrogen. Sorry about that. In this case, they both get their way, so it doesn't really matter. Since we do have the oxygen as well. At this point, the oxygen has to be whatever it has to be in order to balance out the charge. So the sodium we should have really assigned first here. I focused on the hydrogen because I wanted to make this point. But sodium has the strongest preference for being +1 since it is in group 1A. Hydrogen being bonded to a nonmetal prefers +1 as well. So in order for our total to add up to 0, the oxygen needs to be -2. It has no other choice. It just so happens that that is what it prefers, and you will often find that to be true, but not always. A couple more. Let's do SO4 2-, OF2, and zinc sulfate. And these will be our last examples that I will just do for you. So SO4 2-, if we look through our list here, both sulfur and oxygen have a preference. So oxygen is here in rule 5. Rule 7, group 6A, includes sulfur. So they both prefer to have an oxidation number of -2, but oxygen's preference is stronger. So oxygen gets its way. So there are 4 oxygen atoms, each with an oxidation number of -2 for a total of -8. We need everything to add up to -2. So that means the sulfur must be +6. OF2 here, we need to remember that fluorine has the highest, strongest preference of all. Ones like this people tend to get confused by because oxygen has a preference and fluorine has a preference that are both relatively strong and are both most of the time granted. But fluorine wins the battle because fluorine is up here in rule 2, oxygen is down in rule 5. So if there are 2 atoms of fluorine, each with an oxidation number of -1, that means that the oxygen has no choice but to have an oxidation number of +2. So our last example is one that's a little bit tricky. Anytime you see something with a polyatomic ion involved, you want to treat your ions separately. So essentially you want to separate this out. You should recognize SO4 as the sulfate ion. In fact, we just did that as one of our examples. And that means that this is zinc 2+. So by treating your ions separately like this is, in this case, the only way to get to the correct answers. Because they really are separate particles. They're connected by an ionic bond, but it's a different type of interaction. So right away, separating them into ions tells us the oxidation number for zinc, because this is now one atom by itself with a +2 charge. So this must have an oxidation number of +2. In our sulfate ion, we already saw that oxygen gets its preference of -2, sulfur is +6. If you tried to solve this one just as is, you would probably think that sulfur is -2 and then zinc ends up being +8, which is incorrect. We know that the sulfate ion as a whole has a charge of -2, so we need to respect that and we need to treat it as that. So whenever you have a polyatomic ion involved, you want to separate the ions and think about them individually to determine your oxidation numbers. So now I'm going to have you pause here and try to do a few more examples on your own, and then we will go through them together. Assigning oxidation numbers is a super important skill to be able to do, so I want you to get lots of assisted practice here to be able to go off and do it on your own comfortably, since you're going to be doing it a lot for the rest of this unit to kind of know what's going on where. So pause here, assign the oxidation numbers for each atom in each of these compounds, and then we will talk about it. Alrighty, so for this first one, fluorine has the highest preference, so its oxidation number gets to be its preference, which is -1. That means that sodium has no choice but to be +1 in order for our oxidation numbers to add up to 0. For the next one, calcium has the strongest preference. It is in rule 3, whereas oxygen is all the way down in rule 5. So calcium gets its preferred oxidation number of +2, which means that oxygen has to be -2 in order for our oxidation numbers to add up to 0. This one, we've got a polyatomic ion, so we want to split these apart and treat them separately. So since we recognize this as the polyatomic ion bicarbonate, we know that that has a -1 charge, which means our silver must have a +1 charge. So its oxidation number must be +1. In the bicarbonate ion, we have hydrogen with the strongest preference for +1, oxygen with the next strongest preference for -2, and there are 3 of those guys. So currently we have a grand total here of -5. We have -2 times 3 is -6, plus 1 is -5, and we need a total of -1. So our carbon must be +4 in order to make that happen. For iron 2 sulfide here, sulfur's in group 6, so it has a preference for a -2 oxidation number, which means the iron must be +2 in this case. The cyanide ion relies on rule 8. Group 5A includes nitrogen. So this has a -3 oxidation number, which means that carbon must be +2 in order to get us to our total of -1. XeOF4 here, both oxygen and fluorine have preferences. Xenon does not at all. So both fluorine and oxygen get their preferred oxidation numbers of -1 for fluorine and -2 for oxygen. So we have 4 -1 fluorines and a -2 oxygen for a grand total here of -6 so far, but we need it to add up to 0. So the xenon has to be +6 in order to make up that difference. In H2O2, hydrogen has a stronger preference. Hydrogen is rule 4, oxygen is rule 5. So hydrogen wins this dispute and gets its way. So there are 2 hydrogen atoms, each with a +1 oxidation state. We also have 2 oxygen atoms that we need to make up the difference here. So each of these must be -1 in order for our total to be 0. So note that oxygen does not get its preference here. This one always messes people up. It is a -1 oxidation state because hydrogen's preference is stronger. So the next one here is a little bit tricky, sort of. If we have 3 atoms and their oxidation numbers have to add up to -1, they all have to be the same, each one has to be -1/3. Yes, you can have fractions. And then last but not least, we have hydrogen and nitrogen. Hydrogen is rule 4, nitrogen is covered under rule 8, so hydrogen wins. So we have 4 hydrogen atoms, each with a +1 oxidation number. We have 2 nitrogen atoms, so each of them must have a -2 oxidation number in order to add up to 0.